Before we start this problem, let's take a look at what it's asking. This is a question about Formula One race cars, and we're told that they speed up much more quickly than normal passenger vehicles, as we would expect. They also stop at a much shorter distance, and that makes sense as well. Now, this particular car is traveling at 90 meters per second, which is about 200 miles per hour. It comes to rest over a distance of about 110 meters. That's just a bit more than a football field. So it sounds to me like this is going to be a very large acceleration. We're supposed to find the magnitude of the acceleration as it slows during braking. Let's do a pre-assessment. What do I expect the magnitude of the acceleration to be? Answer, big. Now, a normal passenger car can accelerate about 1 G. I'm expecting this to be a few Gs. Okay, that's kind of what I'm looking for here. So with our pre-assessment in mind, let's go ahead and prepare to solve this problem. And we're going to prepare by drawing a picture. And the particular picture, which I want to do, is do a pictorial representation. And on this pictorial representation, I'm going to list the values. So I'm going to combine the pictorial representation and our table of values. Now the car starts right here at a position of 0 meters. It finishes at a distance of 110 meters. That's our stopping point. It starts at a speed of 90 meters per second. It finishes at a speed of 0 meters per second. So from here to here, as it goes from 0 to 110 meters, it's slowing down. The acceleration vector must be directed to the left. So when we compute the acceleration, it will be negative. But we're interested in the magnitude of the acceleration, so the negative sign won't matter to us in the final result, but it's a good check on our work as we proceed. So the car goes from here to here. It slows down from 90 meters per second to 0 meters per second. The acceleration is directed to the left. We're asked to find the magnitude of the acceleration. We don't need to know anything about the time. We're not told anything about the time. And so the easiest kinematic relationship to use is the one that involves velocities and positions, but doesn't involve time, the one that looks like this. The final speed squared is equal to initial speed plus 2 times a times the final position minus the initial position. With that relationship in hand, we're ready to solve. And the solution is pretty straightforward. Here's our basic relationship. I'm going to rewrite it this way. Vf squared minus Vi squared is equal to 2 times a times xf minus xi. Now what we're trying to find is the acceleration. This is what we're looking for. And so I'll just do some algebraic manipulation and come up with this. The acceleration is equal to 1/2 Vf squared minus Vi squared divided by xf minus xi. Now here's the thing. We know all of these values. The final position is 110 meters. That's right here. The initial position is 0 meters. The initial velocity is 90 meters per second. The final velocity is 0 meters per second. So we know all the values to put in this relationship. It's just a simple matter of computing. And if we do that, we come up with an acceleration of negative 37 meters per second squared. But the question just asks for the magnitude of the acceleration. The magnitude of the acceleration is just 37 meters per second squared. That's what we're looking for here. Now, as a quick check on our work, this is approximately equal to 4 Gs. And we suggested at the start that we'd expect the acceleration to be quite large. Normal passenger vehicle can do about 1 G. This car is doing about 4 Gs. And so the acceleration is large as we would expect it to be. And so our final result matches our understanding of the way the world works.